Hello, welcome back. In this video, we're gonna solve the bounding problem in CSAPP datalab. So the question is, if the input number is 0, then we should return 1. If it is not 0, we should return 0 here. We are limited to only use bits operations here, and then the maximum number of operations we can do is 12. So as we mentioned, the bind operation or the logical not operation of a variable is really equivalent to saying if x is equal to 0, then we return 1, otherwise we return 0, right? This also is equivalent to, let's say, let's just change the order of the return value here. So if x is not equal to 0, then we return 0, and or otherwise we return 1 here, right? Here, this x not equal to 0, if we looking through length of bits, then it also really means if x has any 1 in its 32 bits, then we return 0, otherwise we return 1 here. So now it's very apparent that the core of this problem is to test whether x has any 1 in its 32 bits here. To test whether x has any 1 in its bits, we can leverage the bit level OR operation. Why is that? Because OR is a, we can consider it's a bit preserving operation. What I mean by that is if we do bit level OR between any two bits, it will result in 1 as long as one of them is 1, right? So if we do 0 OR with 1, then we get 1, and then vice versa. This operation only results in 0 if both of bits are 0 here. So based on this observation, a intuition is if we can use another helper bit to scan through the variable x here, and every time we use this helper bit to do bit level OR with the corresponding bit in x, and then store that result back to this helper bits. Then at the end, after we scan all the 32 bits of x here, the value in the helper bit here should tell us whether x has any 1 in it or not. As long as one of the bits in x is 1, then this helper bit should be 1 at the end. Okay, let's write down this first idea here. Let's call this naive brute force solution. We're gonna use a helper y starting with 0. I'm gonna scan through the x here, so do 32 times, and then each time we do y equal to y or x, and then we shift at the end of each time we do x equal to x, shift right by 1 here. So what does this do is really every time in, let's say, in iteration I here, we are only using the last bits of y here. All the other bits we don't care. So y's last bit tell us if there is 1 in x position 0 to I here. Right here, as at the end of this repetition, y's last bit, if this is equal to 1, it really means that x position from 0 to I, those bits, at least there's 1 in it. And then we redshift x by 1 at the end of every iteration here. At the end here, y's last bit tell us if there is 1 in x 32 bits. In other words, if y equals to y's last bit is 1, then x has 1 in it. Otherwise, x doesn't have 1 in it. And then a trivial last step is to flip the last bits of y here in order to match this 0 and 1 value. So with this, we are able to tell by using redshift and bit level OR to tell whether x has any 1 in all of these bits here. This logically should give us the correct answer, but there's one problem. So we are doing these iterations 32 times here. In each of these iterations, we are doing 2 operations, right? One is a bit level OR, and then the other one is a redshift by 1. In total, this will give us 2 times 32, so it's 64 operations. This is well beyond the maximum allowed operations here. So obviously, we need to improve this solution. The core part of thing we are doing here in this solution here is we are essentially processing only 1 bit in each of this each of this iteration here. Can we do more than 1 bit per iteration? So notice that this OR operation here is not only processing 1 bit per time, it's actually processing all the 32 bits from both of the variables, but we are only looking at the last bits every time we do this. We are essentially wasting all the other 31 bits processing in each of the iteration. So how to do more than 1 bit every time? Let's start with a actual example of one here. Okay, let me copy paste this. And let's call this a improved solution. So let's start with a example of x equal to let's say 1100 all the way down to let's say 1010. In total, there's 32 bits here. It's 32 bits. What if we break this number into 2 parts, right? So the first half is the left 16 bits. It's 1100, and the rest of them. So this is 32, and then the second half is all the bits in front of this, and then 1010, right? And if we do the OR for these 2 halves here, the number we get here is 1100. Sorry, 11. We don't know whether the other 2 are 0 or not. And then at least is 1x here, right? This x can be 0, can be 1, depending on the last 4 digits here in the first half. So we get this result here. What this means is array 1 tell us whether if there is 1 in the corresponding position from the 2 halves here, right? And this result is 16 bits here. What we did just now is to condense the information for whether x has any 1 in it from a 32 bits representation to a 16 bits here, right? So condensed to 16 bits. From here, we can really generate this solution, saying from 16 bits, we can further condense it into 8 bits by doing another halving process and do the OR here. So the same information will be condensed further from 16 bits to 8 bits, and then all the way to 4 bits, 2 bits, and 1 bits, right? So let me write down. So do this condensing do this halving and condensing from 16 to 8 to 4 to 2, and then at last to get 1 bits here. So let's calculate how many operations we are doing in this solution. Every iterations here, we do this half and OR. So by shifting the half, we are really using this redshift to 16. So we do this redshift operation, and then we do this OR operation. So there are still 2 operations per time. and then we do the iteration 1, 2, 3, 4, 5 times here, right? So in total, there will be 10 operations in this main body of a solution. Compare with this previous brute force solution, which has 64 operations here. The new one is much faster and is below the maximum allowed number of operations here. With that, let's translate this into code. Okay, here I have the code written out. Each of these 5 lines here represent one iteration in the previous algorithm. In each of the iteration here, we do first we do a shift, and then we do a bit level OR, and then store the value back to X here. At the end of each of this iteration, the corresponding bits, last like a number of bits, in this case is 16 bits, is the condensed representation of the information of whether X has ones or not. At the end of the last iteration, the last bit of X represent the entire 32 bits of whether it has one or not. And then at the very end, we need to flip the last bit here, and then in this operation, we flip the entire number X, all the 32 bits, and then we do a AND operation with a mask, which is a constant number 1, to extract out the last bits here. With that, we can test out the solution. So we do make bit test, and then we do bit test bang here. So yeah, it passed all the test cases here. In terms of number of operations here, as we mentioned before, each iterations we have 2 operators, and then we have 5 iterations. Then in total will be 10, and then plus this last 2 operations. Overall, we have exactly 12 operations, which is the maximum allowed number of operations here. Let's verify that by running dlc-e vids.c. Yeah, here you verified our calculation here. We in total have 12 operations. With that, we have solved this problem. Hopefully you learned something from this video, and I will see you in the next video.